All right, welcome to Thermodynamics. Still talking about heat cycles. So we'll actually talk entropy next chapter, which is coming up next week. I have a problem here. There's a Carnot heat engine, and there's some things you want to find here. We're going to do an example of that. So, it has a high temperature reservoir, 652 degrees centigrade, kind of funny number, and the low temperature is room temperature, basically, which is usually the case. We know that this much fuel is coming. Basically, there's an energy flow rate. That's basically our fuel is 500 kilojoules for every cycle of the engine. So it's not a power thing now. It's a work. It's a how much, not how fast. The kilojoules is a how much. So every cycle of this engine, that much and that much energy is getting sucked out of the high side. It's producing some work, and some exhaust, waste exhaust, goes into the low side. So, question number one, I want to find Carnot efficiency. So, what should my formula be? Can anyone recall from yesterday? This is the one you should have had tattooed on your eyelids overnight. Yeah.
One divided by
Right.
PL minus 1.
Is one for the heat engine. It was 1 minus T low over T high. For refrigerator, it was more like what you were talking about. So great. 1 minus 30 over 652, right? Somebody say wrong.
Wrong.
Excellent. You're on the ball. For Carnot efficiency, it's like ideal gas. It's about absolute temperatures. 30 degrees C is not an absolute temperature. 30 degrees Kelvin would be really, really cold. This is going to be 273 plus 30 makes it 303. Which makes the units cancel. Efficiencies are ratios, so there aren't units for them. So that's a 5, that's a 25, 65, and 27. I don't know. $925 sounds good. So 303 divided by 925. Subtract that from 1. I must be pushing something 60-some%. Carnot efficiency. Say again?
67.2.
Thank you. 0.672 or 67.2%. If you have an issue with percents versus digital numbers, remember, all this really means is percent. How many cents are in a dollar? American dollar? Is it 17? 172? Close to 100? 100 cents in a dollar. Per cent, per 100, literally it means per 100. 67.2 per 100. It's like that's all percent means. So you just slide the decimal point over. And so now we got 67%. What does that mean? That means my efficiency is, what we wanted was the work. Oops, I got my arrow wrong. The work coming out of the system net work over Q in, or call it Q from the high side. Since I called the other one low, I'll call this one high. Is that. That's true for any kind of efficiency. In this case, we're specifically talking about the Carnot efficiency, which is a thermodynamic limit. So if I want to know how much work's getting done, I could say the net work produced by the cycle is efficiency times the QH, because it's 67% of the energy flow from the hot side. And therefore we got, I don't know, 36, yep, that sounds right. That's the most we could hope to get, and that means doing conservation of energy on my diagram up there. We got 500 in, we got 336 coming out. My Q low is going to be equal to Q high minus net work energy. Now Q low and Q high are actually heat flows. The work net coming out it was converted into some kind of motion probably. So they're different. It might be different kinds of energy, but they will add up. So 500 minus 336 kilojoules is going to give us a exhaust heat of, well, what do you think, 164? So that's how that can work. Again, we're just given temperatures and heat flow, and from the temperatures we were able to figure out the Carnot efficiency. And always remember, always with ideal gas and always with Carnot, which I guess would be based on that perhaps, it's in absolute temperature. Next one, I think I'm not going to go all the way through this in class just because there's quality things, but we'll talk to it and I'll probably work it out and post the example. But this one we're doing R134A. We can do a Carnot efficiency pretty fast because we have that, but again, we have to do it in terms of ideal or temperature. But this is a refrigerator, or maybe it's a freezer. Low temperature is -8 degrees. High temperature is 20 degrees C. They gave us the temperatures, and they're doing this inside of the saturation dome. One reason for doing that is it does give us Carnot efficiency said the heat flow all has to happen at a constant temperature. And so when you're in saturation, you're changing phase, and by golly, that meets that criteria for Carnot of a constant temperature low heat, a constant temperature high heat. In this case, you bring it up, and you can do a constant entropy process here, adiabatic and reversible, slow enough reversible, whatever. If you do this as a compression, as an adiabatic compression, to the point where you get to saturated vapor, and then you cool it off and it becomes saturated liquid, and then you adiabatically expand it. You can approximate what the limits for Carnot are. So that's why they're doing it inside of the saturation dome. If we know this temperature, what do we know about the pressure? And this is 0.3, that's actually the high temperature. So is it possible in saturation? Do we know what the pressure is just by looking it up?
Yes.
So that one's pretty simple. Quality at 0.2. Oh boy, how do we find this point? That's the trick. That's one reason I don't want to do this one quite yet, because it's introducing us. If we know that this point is supposed to be saturated vapor, there's a value for entropy that goes with this temperature and pressure, that state. It has a value for entropy in the tables. If we then find at what point you can have that same value of entropy at this pressure, which is at saturation there, it's going to have, there's going to be, between here and here, and if it has the same value as it does up here, then you can, this process being isentropic, meaning the same entropy, so this entropy value is in the table, so is that one. And we just have to find what quality we get, because now that these values are going to be more spread out. We can find the quality of 0.1 and 0.2 in order to from this entropy. And then if we know the quality, we can find the enthalpy, we can find the volume, we can find all that stuff. When we're all done, we can figure out all those states are. Actually, the easiest way to deal with this is as a Carnot refrigerator. It says you're going to have a perfect, the efficiency can be determined according to the Carnot relationship for a refrigerator, which is a little different than the one for an engine, but it's related to T high, T low, and ones, and I think on refrigerator it's upside down and so forth. That was a couple slides back. If I go to 0.3 to 0.4, the saturation value is there from here to here. That's the HFG at this temperature. That's Q out. I know the Q out and the work in to get the Q out, and then this would be Q out plus Q. And anyway, we can just wrap it. We don't have to actually get all of the points here, but once we know the Carnot efficiency, then if we know this Q high, we know the efficiency, we can come up with Q low, and come up with the amount of work, undo the problem. And the next thing we get, if this is the amount of work that went in, if we know the work was, actually that's another thing, this would be work in as kilojoules per kilogram. And now we know how many kilograms, we can figure out the scale of the system. But this one has enough sort of weirdnesses going on that I'm going to work this one when I'm not just standing in front of you under the bright lights. I do want to spend some time talking about lab today. And we'll see how much more time we have after I talk about it, to talk some more about this chapter, chapter 7. But lab today is an air motor lab. It's probably the most, I don't want to say complicated, the most thermodynamic lab we have. So I want to talk about it a little bit. So what's going on? We have a water system. We've got a pump. There's a pump. The particular type of pump it is called a gear pump. It's like oil pumps in cars are the same thing. There's teeth that mesh and they turn around, and they're in a tight-fitting cavity. And as the teeth mesh, there's like fluid in there, and the fluid gets carried around the empty teeth as they go around the outside, and where they mesh, then they kind of squirt the fluid out, if you want to think of it that way. And the teeth meshing prevent the fluid from going from the high pressure side to the low pressure side. And what it does is it creates flow. And if you give it a restriction, it will cause, in theory, it causes the same amount of fluid to move forward each time it turns around. And if you create a restriction, it just jacks up the pressure until something breaks. So there's a pressure relief in it. There's also the fact that you can't perfectly seal it. So what really happens, instead of always having the same forward motion, as you increase pressure, some of it squirts back through the seals or around the seals or around the teeth. And as a result, as the pressure goes up, it does deliver a little bit less fluid because some of the forward motion, with more pressure, it leaks backwards. So it's a type of pump that you'd call like a constant volume type pump, and what it generates is flow, and the pressure is based on the system restriction. So that's being turned, and so what we want to know is the basic name of the lab is the first law lab. That's what I'm calling it because it's energy balance, but now we're instead of energy balance with R134 cloud in the air and that sort of thing. Now it's about this fluid. So if we have a system, it's a system, and one side of the system is creating water energy. And what's the water energy or flow? The power in the water is, and you remember what the water power might possibly be? It was in your test, yeah? Delta P times the volume flow rate, yeah. Pressure times the volume flow rate. We are going to do it for a number of different pressure points. Free flowing, 20, 40, 60, 80 psi. So each group will have 5 data points. Trying to remember how I split. Every group has a different set of data. I think I'm trying to remember well, let's get the rest of it. So that's the water power. On the flip side, have an air motor. And when it's going unmuffled, it sounds like a gasoline engine or something. Put, 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 put. It's a vane type motor. there's a cavity and there's a rotor, and the rotor's offset in the cavity, and there's spring-loaded plates that kind of slide in and out as it goes around. And the pressure pushes on one side of the plate, pushes on both sides actually, but one side will be seeing exhaust, and it's exhausted to the atmosphere, and the other side sees the high pressure, and it's trying to push on the plate, and that's what rotates the motor. And the plate gets larger and smaller, and high pressure, low pressure, whatever. There's not just one plate, it's like, I don't know how many, 8 or 6 or something, that as it goes around. And we're applying compressed air to it. So, oh, and by the way, we have a control valve on the water system. And the water's circulating counterclockwise there. Water sucks in here, and we're measuring pressure on the inlet and on the outlet of the pump. It turns out the inlet side is going to go more and more negative. It's sucking on this side, so we have to make sure it's pressure difference, because this side can drop 1 or 2 or 3 or 4 psi, and if you're talking about 20 psi, that could be, 20% of your total pressure difference. So we need to watch for that suction side. The difference in pressure is what the pump's doing. Why? Any ideas why this might go from like a neutral pressure to suction, basically negative pressure?
Because you're pumping liquid out of the pump.
You're pumping it out of the tank, and the tank has a hose. And if you ever tried sucking, if you've got a milkshake and you want more, it to come faster, you have to suck harder on it, right? And so, depending on the length of the tube and the size of the tube, you have to suck harder. What does that mean? You have to suck harder. This is going to be a lower, if you don't suck on your straw, you're not going to get anything out of it. So you're creating a negative pressure relative to the surface of it. So, same thing here, it's sucking through a straw. And we'll be measuring pressures on both sides. And we'll have a flow meter, a volume flow meter. It's literally, they're called rotometers. And it's a cylindrical chamber. And in the middle, in the chamber, there is a float that doesn't float. I mean, it's a metal shape. And as you have more flow, gravity's pulling it down, and fluid drag going up. And when they balance, because as the chamber gets bigger, there's more room for flow to go around, so it slows down. It comes to a balance point, and you can balance it at one flow rate, it would balance here, and another flow rate, it balances up the gravity and the drag balance, and you can calibrate that, so there's a scale on it that scales how much it rises or falls, tells you the flow rate. So we have one of those for the water. We also have one over here because, well, on the air motor, there's a coupling between them. Air motor is turning the pump. We've got compressed air. And we have temperature here and temperature there. Compressed air goes in, you control the amount of power in compressed air with this. What varies is the RPMs. Each group will be doing a different RPM. You're going to try and keep it close to, it doesn't have to be exactly, if I say you do 900 RPM, you don't have to do it exactly 900. It would be impossible to keep it there. Just things like the motor, the air motor settling in, it takes time because the temperature, this is like the whole thing about settling in and come to up to temperature. It takes time for this to settle into a new load, and so you're gonna. If I tell you 900, then you're like 880 to 920, but you have to make you make sure that you record exactly what the RPM really is. Because that's a crucial point, but you're going to be assigned, do it around 900 RPM. There'll probably be groups like 50 or 100 RPM apart. And temperature in and temperature out. And over here we've got a temperature and another flow meter. Now, energy in is coming from compressed air. So the power is going to be mass flow rate times H, call that 0.2 and call this 0.1, 2 minus H1. Anyone remember how we find the change in enthalpy for an ideal gas? We look it up in a table, we use a formula. Anyone remember about C sub P?
Mass times C sub P times delta T.
Yeah, this becomes C sub P about delta T. What about pressure? We said this will get us there, but we know there's pressures there. What about the pressure? Oh my God. Do we need pressure? If this was at really high pressure and it expands, what's the temperature on the outside? What happens when you expand a gas? Does it heat up? Does it cool down? Yeah. It's cooling down. It actually does work, and the fact that it cools down says that it expended some energy somewhere. It did it in turning the shaft. The funny thing about air motors, on the way in, when the air was initially compressed, it was compressed and it went into the tank, wherever the tank is in this building. It's piped all over the building. We have a drop right there for compressed air. But it went into the tank hot, and then it cooled down to room temperature. And then it comes through the pipes, and the pipes are all at room temperature. It comes to your place here at room temperature, then it expands. What do you suppose the temperature on the outside is going to be? It's going to be hotter than it went in. If it's hotter, it means it gains some energy, right? Well, air motors, actually, the outside can come off cold, actually, like refrigerated. It'll frost. Some of you, not all groups, but the groups with higher RPMs, will probably come out frosting the outlets. Temperature drops. So, it turns out that the temperatures kind of report that whole pressure thing. It is about pressure times volume. We don't know what the volume of the pump is, but we can do this C sub P times temperature, and we don't need to measure the pressure. Now, there's some neat things we could do if we did have pressure measurement on either side here. We could use our isentropic, with the things that we'll be learning in a bit. We could come up with the isentropic efficiency of the air motor and stuff like that, but that's not part of this lab, so we won't worry about that. C sub P times the delta T across the motor times the mass flow rate gives us power. How do we get the mass flow rate?
The flow rate coming out of the muffler.
Yeah, out of the muffler, it's going to tell us the volume flow rate, but not mass. It's all about volume. It's the same thing. It's a chamber that Not temperature for mass on that one, but we got a volume flow rate. Times density. What is density? Density is mass per unit volume. So mass per unit volume times the volume flow rate should get me a mass flow rate.
So the density depends on the temperature of the.
And density would depend on the temperature where you're measuring the volume flow rate. So there's a temperature probe in the muffler tank that tells us what temperature the volume flow rate is being measured at. Next question: How do we get that density? Do we look that up in the table, or this is ideal gas again? Nice thing about ideal gas is you don't have to interpolate off the table because there's a relationship. PV times RT, but V is, this is oops. Specific volume is the inverse of density, so we could also write this as P over rho equals R for air times T. And that means my density, bring this up as P absolute over R air times T absolute. So if you incorporate this into this equation and all that up into here, we should have everything we need to find the air power being furnished to the motor. The air power that's actually using. If that's the case, that's power in, and this is the power out. We can find an efficiency for the entire system of the air motor and the pump. We can't separate how efficient the pump is, how efficient the motor is. They're bound together. But we can say, we put this much air power in, it turned into this much water power. And we do that at different RPMs for each group. And the thing about this lab is you got the water power thing going, and you actually have a thermodynamic process going on in the motor. Industrially, a motor like this would be good if you, they do use them in industry, especially if compressed air is already available, but also if you don't want sparks because something might blow up. And most of the time, if you have an electric motor, you can have an explosion-proof electric motor where it's sealed so there's no sparks. But if you put a load on it and it has inefficiencies, that shows up as heat, and now it's adding heat to that zone. Whereas something like this, it's doing some work, and then it's also cooling things down instead of heating things up, which there's process things where maybe it could provide some refrigeration. If you're pumping something and you need to also condense, like the biodiesel plant. They don't do this there, but they have to evaporate methanol to recover it. Well, if you're pumping with an air motor, you could be using the exhaust to run through the condenser and help condense the methanol that you're pumping the fluid to the hot zone for, or what have you. So sometimes I can imagine cases where this would be useful. So in your lab, that's why you'll have, it says lab 5 in the Canvas, but the thing says lab 6. At any rate, it's the lab about the air motor. So you're taking pressures here and pressure there. Do we care about the temperature of the water? Not a whole lot. I mean, it would make it will affect how the flow meter is calibrated if the flow meter was super crazy calibrated, but for approximate room temperature water, it doesn't make a big difference. So we don't worry about temperature on the water. It might make a difference because the water temperature will vary or the density does vary with temperature, but the temperature is not changing much. The biggest problem with this is if this generates air bubbles and you end up with a bunch of air bubbles pumping through here, that will definitely affect your reading. So you will get some of that, but be aware that you want to avoid that because that'll change this reading. But we don't care about temperature over here. It's all about pressure in, pressure out, and what the volume flow rate is. On this side, have temperature in and temperature out. Turns out we don't care about pressure for what we're doing because we don't need it to do this equation. We do care about temperature when we take the flow. And you know what else we need? There's a temperature there, and there's also, what else do we need in order to do our density measurement? We need the density at the point where we're measuring the volume flow rate. This is a constant. We're measuring temperature. Should we also measure pressure there so that we can get all of that data? So your data sheet says temperature, pressure, and that pressure, want to make darn sure it's an absolute pressure. Because if it's not an absolute pressure, we could get a gauge pressure, but then if we don't know what the room pressure is, we could be off. That would be a source of error. So, there'll be a handheld tachometer here that we use to read how fast the shaft's going. And the real trick is you add the load, and then you add some power, and then you're always in this balancing job. When you finally get it back in balance, and then you have to wait for it to settle, then as it settles, it kind of shifts a little bit as the temperatures adjust. And I haven't figured out a really good way to adjust to. I mean, it's just something you have to get a knack for. Basically, probably the best bet is to have somebody operating both the load valve here, because basically what happens with the pump, it's creating a volume going forward, and the system pressure it sees is, as you close a valve, it's generating a back pressure. It's generating a resistance, which causes a back pressure. If it causes 15 psi of back pressure, that would be equivalent to as if it was pumping something up 30 feet or however high. We're creating an artificial load. And how does that power get dissipated? Well, the water going through there kind of squirts and generates heat within itself. It's not going to generate much, but that's what's going on. Instead of just pumping it up 30 feet, we're generating the various pressure to 20, 40, 60, 80 psi. So we're creating a load with the output valve. We're giving it more power with the air valve. And it can be pretty tricky to try and hit both the pressure outlet and the RPM you're going for and wait for it to settle. Because if you just get it going and you don't wait long enough, the temperature, you want the outside out temperature to stabilize. It'll start changing, and it'll keep changing until it levels out. And I don't know how long that takes. Probably depends on how much of a load you have. So that's what's the lab for today. Is that making sense to people? It make a lot better sense when you have your hands on it. Then it'll be all pandemonium. I'm not done. I'm just making sure we got people talking about the lab.
There's 9 different measurements we have to account for. This is 9 there.
Yes, basically. And that's one of the tricks. You probably want to set up so that one person takes the data and somebody's involved, somebody's reading the flow meters and somebody's reading the temperatures or pressures, or, you know.
How big can
Too big, it doesn't help. We're talking probably 3 or 4 people or whatever. One person's doing the controls, and when the controls are good, and actually that person could be reading a couple of the things, because you're going to have to wait for it to stabilize. But yeah, 3 or 4 people in the group. If you get too many more people than that, you don't really get a sense of what's going on. But there's 9 data points for 5 conditions at a given RPM range. It's kind of fun, actually. I mean, when you're all done, you know, my job, every group, you give me data, and I'm going to take the entire class worth of data and compile it. And you'll see your curve will, at 1 RPM, the flow rate goes from here to here, another RPM goes here to here, another one kind of there to there, and you can see them all kind of stack up. And I'll also push the analysis farther than what you guys are doing to come up with things like there's some unexpected things you can get out of with the efficiency data, like what the torque, the friction torque of the motor pump is, the inefficiency part. The efficiency will kind of peak out and it'll kind of level down to a point, and you can predict what the torque of the motor is. And you can see setup 1 and setup 2 have basically different torques based on how tight the packing nut was tightened down on water pump. You'll give it more friction, and you'll see that in the data. Oh, I did manage to use it the whole time. All right. So that's what's going on in lab today. And that's it.